Good day, everyone. So this is your Creative Technologies 10 video lecture 1. I am Sir RC, and once again, good day to all of you. It has been a long time since we had our discussions on Creative Technologies 10, and I hope that you are safe and sound in the comfort of your own home. So, for today's video, for today's lecture, we will review some of the concepts that we have talked about in our previous sessions, and we will expand our knowledge towards the concepts that are included in this part of our lesson. Okay, so let's start. Again, we are in a boot camp, technically, the physical computing boot camp. And we will be looking at what is physical computing. It is the art of building interactive devices that can sense around its physical world and react with a physical action. Of course, there's always processing behind this sensing and reaction. Okay? In our core model, in the physical computing, we have inputs, the processing or process, and the output. In the output, we sense the world, we look at different physical parameters that we can gather, that we can measure, so that we can create informed decisions. Those informed decisions are then made in the processing, in the process stage of our model. And then from the processing, we will continue to the output. What do we do with the inputs and the processes that we have made? All of that is controlled by our brain, or in our case, the microcontroller, where it sends signals to gather information around the world, around its physical world, basically its inputs, and then use the code that is in that microprocessor to process the information, process the inputs, and then after that we have the outputs that is also controlled by our brains or the microcontroller. Now, our microcontroller of choice for the duration of Creative Tech 10 will be Arduino. There are other platforms for physical computing, but for our case, we will be using Arduino because, first of all, it's open source. Anyone can contribute, and there is a very large community of enthusiasts, of hobbyists that are supporting and using this platform. Okay, so it has main component. First, the circuit board itself, the hardware that houses all of the physical computing, the physical computing, and the software, the computing side, where we have the code for our microcontroller and our in between, the integrated development environment. For now, we will not be using the IDE or the Arduino IDE, but we will be understanding how does it work by building code for Arduino. Now, in our case, where we can't physically interact with Arduino, we will be using a virtual lab called the Tinkercad circuits. I have asked you to create your accounts or to use your accounts in Tinkercad circuits. I have given you the credentials, and hopefully you can open the platforms for yourself on your own devices. We will be using this web-based simulator to create, program, and test virtual prototypes of our electronic projects. From the simplest Arduino blinking light up to the most intricate things that we can, we will be using Tinkercad circuits. Now, why do we need to use, for our case, why do we need to use Tinkercad circuits? First of all, we are in an online modality, so I can't send you, each one of you, a whole kit of Arduino, but if we can, why not? But for now, it's not. But for the main purpose of Creative Tech 10, we will use a simulation first strategy. Here in simulation, in this strategy, there is no risk. You can change components. You can change the components and not break anything. You can't break or burn out virtual components. You just simply swap them out. It doesn't work in this environment. It works or it doesn't. Okay? This makes for a perfectly safe place to experiment and learn from your mistakes. The nice thing about Tinkercad circuits is that it shows if it burns out an LED or it doesn't work. All of that is zero risk. You're not burning any physical material for that. It's just a simulation. Next, due to that thing, because we are not burning out physical components, it's almost zero cost. It's almost zero cost. Of course, you will be using internet. You need an internet connection for that because it's not offline, but it's almost nothing. It's almost zero cost. And most importantly, we can focus on the fundamentals of the circuits. By using a simulation first, we can concentrate purely on the principles of the circuit design and the logic of code before putting it to the complexities of physical wiring. We can use this as a test bench. We can use Tinkercad circuits as a test bench before we go to the physical circuits that we have. Okay? So we will be jumping in to how do we instruct the Arduino platform. Okay? So let me show to you. Let me show to you our Tinkercad platform. Okay, so this is me acting like a student so that I can demonstrate to you what does it look like if you are in a PC or computer. If you are using a smartphone or a cell phone, it could be a different experience. And this will be our first activity. This will be an exploration activity, but I'm encouraging everyone to copy and tinker on it. Okay, I will be taking note of everyone that has copied and tinkered around the given circuit. Okay, I have made this circuit for you, so you have to copy and tinker for yourself. Okay, so it's now actually in your Tinkercad classrooms. Okay, well, you can copy it and tinker. You will be copying and tinkering on this one. Now, once you reach this part, you will be greeted with two different Arduino boards. I have two Arduino boards and one a simple circuit. The second one will be more components, a little bit more. We'll use that as an example. And later on, you will be tinkering it on your own. Now, here, our Arduino will be clicking on the first one, the single LED, and then let's look at the code. Okay, we'll be enlarging this one, and yeah, this one. Yeah, right here. We have here the code that is running on this single LED Arduino. Let's name this circuit or the Arduino setup as single LED. Now, the code, the instructions that will be running on this Arduino board is right here. Now, it is written in C++. If any of you is kind of savvy in programming, it's nearly identical to C++ in the sense that we have your voids. These are your somehow functions. Okay, now, okay, now the code that is running in our Arduino board is what we call a sketch. Okay, we have the set that will be our set of instructions to our microcontroller. Now, every sketch is built upon these two essential functions. Every void or every space is a function that controls how our Arduino runs. Okay, so we have our two essential functions. First is your setup or void setup. TLDR, this part runs only when the Arduino first powers on. It starts first. It is the setup instructions. And then we have your void loop, by the name itself, loop. It continuously runs over and over again. And this will be the meat, the bulk of the instructions. It would contain the bulk of instructions for our Arduino. Okay, so once again, let's look at void setup. Okay, we have void setup. It contains the preparation block. It is the preparation block of your Arduino program. The code inside this function is executed only once. At the startup of your Arduino, it will read void setup. What is the instruction inside this part of your code? It is executed only once when the Arduino is powered on or reset. There is a button in the Arduino that once you press it, it resets and reads the whole code once more. Its primary purpose is to initialize the settings, such as telling the board which pins will be used as inputs and which ones will be outputs. Okay, so we'll be looking at our example we will be looking at our first example, where right here we have your void setup. The simple one is pin mode. We have your first line, we have your, okay, sorry for that one, I have to repeat that. Okay, so we have your void setup, and inside this block of void setup, we have your pin mode. Pin mode LED built-in, comma, output. Now, what does this pin mode say? We say that the pin that is connected to our LED that is built in right here, that built-in LED right here, that will become an output. Basically, at the very start of our code, we are telling the Arduino, hey, the pin that is connected to the built-in LED will be programmed as an output. It will output 5 volts. Or it will output. It will be used as an output. Now, all of that should be in the void setup. We are telling what should be set up. What are the pins that will be used? What will be the functions of the pins that will be used? Okay, so all of the setup, all of the basic instructions for the setup should be in the void setup. Later on, we will be introducing variables. We can include that in void setup, but most times it is outside the void. But main instructions about the setup of our Arduino is in this code block. Next, we have your loop function. We have your loop function. By the name itself, it is looping. It is repetitive. The loop function contains the main logic of your program. Every bit of instruction, most of the time, it is inside the loop function. After that one-time void setup function runs, the code inside the loop executes repeatedly from top to bottom forever. While the Arduino is turned on, it will constantly and repeatedly read and execute the code that is in the loop function. This endless cycle allows your device to constantly check sensors and control outputs, enabling it to react to the world in real time. Because you have to check in so that you can respond, so that our board, Arduino, our device can respond. It should be checking constantly, again and again and again, checking for physical phenomena, checking for the inputs, processing that information again and again, processing new information again and again, and then responding to the new information again and again. So the input, process, output is repeatedly done in your loop function. Now, let's go back to this one. In our void loop, we have here this function. We have what we call digital write. We tell that, hey, we are writing a value, we are outputting something. Now, where do we output it? Through our LED built in. Now, in our Arduino, the built-in LED, I forgot to say this one, but the built-in LED, this one right here, is connected to pin number 13 or D13. This one right here on the right side. This one. So, we are writing on the LED built-in, or we can say on pin 13. We are outputting on pin 13 and we are outputting an high. When we say that it is a high output, it is automatically a 5-volt output. Okay? We are outputting for 5-volt output. We will delay for 1,000 milliseconds because that's the time unit in Arduino. It is in milliseconds, not seconds, but rather milliseconds. We will say delay, wait for 1,000 seconds, and then we will write it again. We will output through digital write on pin number 13 or on the built-in LED pin. Now on this time, after this time, it will be a low. A low is defined as 0 volts. Arduino works on outputs from 0 to 5 volts, and later on we will understand how does it go from 0 to 5, what are the in-betweens, how does it move in betweens. But for now, if we are telling the pin to go high, it goes for 5 volts. If we tell a pin to go low, it is 0 volts. And then we delay. And then we delay again for 1,000 milliseconds or 1 second. Now, as you notice right here, our built-in LED will blink for 1 second, will display a light for 1 second, turn off for another second, turn on again for another second, turn off again and again and again. because these are the instructions inside the void loop. Output 5 volts, wait for 1 second. Output 0 volts, wait for another second, and then do it again. Now, this instruction is also carried out to pin number 13, because again, the built-in LED is connected to pin number 13. Now, we have here our circuit. We have a wire running to our breadboard, powering our LED. We have a resistor that is somehow protecting or limiting the current that will come into our LEDs. So later on, we'll be understanding these different components. So once again, we have your void loop. We have your void loop and your void setup. In your void setup, all the things that has to be run for the first time, the things that are needed to be set up, those are in void setup, as the name suggests. And then every instruction that needs to be looped, that needs to be repeated so that the function will be done, that is in your void loop. Now, let's go to where all of these components are in. Enter the solderless breadboard. Wait. I am experiencing a bit of a trouble here, so yeah. Okay, so we're back. We have our solderless breadboard. Now, it will be our test bench, test bed in building and testing our circuits. Your sketchpad for electronics. The good thing and the key thing here is it is solderless. You will not have to make permanent connections. You can plug in and plug out components as you see fit. It is perfect for experimentation and correcting mistakes. In physical computing, in creating circuits, you will need a lot of patience, most especially in checking your connections, in physical debugging. So let's get to know the solderless breadboard so that we know its quirks and abilities. Okay, so let's look at the breadboard and let's understand how do we use the breadboard. First, here is a mini one. It's not the full length, but for the sake of illustration, we will be using this one. So this is our breadboard, and we have our first, we will look at the power rails. It is here highlighted in red. Okay, we have two sets of rails at each side. We have your red line right here at the very outside. We have your red line and then your blue line. All of that is connected. We have here your one long connection in all of these points. So if you are to connect one wire here at this point right here at this spot, and you are to connect another component here, if you are to connect one component from at this point and another component at this point, they are essentially connected by that long rail. The main purpose of that is to use that as your power highway across the circuit. This will be By convention, we will be using this line right here as positive. Okay, sorry. This line right here is the positive terminal, and this one is the negative. That simplifies things because you can just plug one one component in the positive rail, and then the other end of the component will return back to the negative rail. Okay, so this long line right here at the very edges are the outside of our breadboard is what you call your power rails. They are connected in this manner. Now, we have here, the next portion is these 5 dots, 5 holes at each side. This is your component rails. It's a bit shorter, but is now horizontal. If we are to view it a breadboard like this, our power rails are vertical and our component rails are horizontal. Each 5 whole row is connected internally. That's why I've highlighted it like this, where all of these lines, all of these holes, 1A, 1B, 1A, 1B, 1C, 1D, and 1E, all of them are connected. So if we have a component, let's say one end of the LED is inserted in 1E, and another component, the power line is connected to 1A. The component is essentially connected to our power because all of the holes in row 1 are connected. So let's look at the example here at Tinkercad. Okay, so essentially we have a wire, we have our wire that is getting its 5-volt power. We are using the red wire right here. The 5-volt power is connected to the red line, the red power rail. As you notice here, it highlights the whole vertical line because again, the power rail is a vertical rail across our breadboard. And then we have here your black wire connected to the other rail of our breadboard. Now, let's turn our focus to the component rails. Pin number 13 is connected to this one, and then the whole thing, this one right here, this horizontal line connects this wire to our LED, to our component. On the other side, we have one leg of our LED that is also connected to a resistor, and then that resistor is returned back to our wire for ground. Okay, so once again, you have your power rails running vertically, and then your component rails, they're running horizontally. Our power rails are much longer and it spans the whole breadboard. Meanwhile, the component rails are only 5 holes wide on either side, and they're also effectively connected. Okay? Now, there is a special part of the there is a special part of the breadboard that is called the ravine or the center channel, and it runs down the whole breadboard and is meant to separate one side of the component rails to the other side of the component rails. Now, it is specifically designed to accommodate integrated circuits. Now, as we have advanced, we have shrunk our circuits to the point that we can package them into these little things called the integrated printed circuits, or if I remember, I can't remember the correct meaning of the DIP, but here, this is your IC. Within it are small circuits that serve a function for our electronics. Now, in our breadboard, it is specifically designed that the space in between the left and the right component rails are enough to accommodate these ICs. It's like right there, like this, where the legs of our integrated circuits can easily insert into the different evenly spaced holes in our breadboard, and in the other side, that can happen too. Here's a different look at our ravine. Again, right here, these black things are what you call your integrated circuits, shrunken and ready-made circuits made for a certain function. And then the ravine runs across our breadboard, and our ravine is spaced perfectly so that one set of legs, component legs of our integrated circuit will fit one set of holes in the left component rail, and the other set of legs can fit perfectly to our other set of holes in the right component rails. Okay, so that is a nifty way of accommodating different integrated circuits using the breadboard. It is designed like that because you don't want these legs to be connected at the same time. You can do so if the purpose of the IC is to be like that, but most of the time each leg has a specific function and they are not to be connected unless the function says so. So most of the time, all of these legs are connected to one side, the other set of legs are to the other, so that these opposing pins cannot be in contact and they will not cause a short circuit. Okay? Now, that is our breadboards. Again, we have your power rails, and then you have your component rails right here. And then this ravine is perfectly spaced to accommodate your integrated circuits. Now, we have your LED, one of the most basic components of physical computing. It's simple. The LED stands for light emitting diode. By the name suggests, it functions and it produces light. Okay, a tiny light bulb. So most of the common projects circling around physical computing, mostly around Arduino, uses the LED because it gives you instant feedback. If you're doing it right, it will light up. If you're doing it wrong, it will not light up, or worse, it will get burnt. Okay, now the LED has a positive and a negative side, and if you interchange that, it will not function, or worse, it will blow up. It not necessarily violent blow up, but it would burn up. Okay, now so let's understand the polarity of the LED. Now, by convention, by manufacturing, we have two sides in an LED. We have what we call the anode and the cathode. Let me move to the other side. Okay, so we have here your anode in our batteries. We have our positive and negative side. In our LEDs, we also have your positive and negative side. The anode is the positive terminal of the LED, and in normal manufacturing circumstances, it is the longer between the two legs. If you are to buy a raw LED on an electronic shop, most often they have long legs, and the longer leg is your positive side or your anode. In conventional terms, in electronics or electricity conventions, this is where electrical current enters through the component. By convention, by agreement, we say that the electrical charges or the electrical current enters through the anode, and it exits to the cathode, our negative terminal. In our LED, it is the shorter. Your anode is the positive side, and then the cathode is the negative side. Now, here's the quickest or the easiest thing, that the most, again, the fundamental things that you have to understand in electronics. First, to make a part work, you have to supply voltage to it, the power supply for your circuit, your push for your electricity to move around the component. Now, in physical computing projects or Arduino boards, when powered through USB, it can provide 5 volts of direct current or DC. But if we need higher power, we can use batteries or different power supplies. Again, if you want a component to work, it has to be supplied but with voltage. Next, you have to facilitate, or you have to make a conductive path for your voltage to flow. The wires itself act as the road for electricity. It connects your voltage or voltage source. It connects your components together, allowing the current to travel from the source to the load. Now, the source, most of the time, when we say source, it is the source of the voltage. It could be your battery, it could be the 5-volt pin in the Arduino. Meanwhile, the load can refers to any component that uses that voltage. It could be your LED, it could be your resistor, it could be your motor driver, and all sorts of stuff. That is your load. Okay, so you have your voltage source, you have your conductive path, you have then your load. This is the component that uses the electrical energy to perform your task. So in our case, the LED is the load. Your voltage source is the Arduino, the 5-volt pin. The conductive path is your wire. The rails in your breadboard, these are your conductive paths. And then your load is the LED. Now, all of that must return to a ground. In the Arduino board, we have here your 5 volts. This is your voltage source. You have your wires, you have your breadboard, that is the conducting path. The load is your components, your LED, your resistor, but all of that has to return to a ground. The floor, let's put it as an analogy. This is the floor of your electrical system. It serves as a common reference point. If you say you have 5 volts, it's high. It's a high. If you say it's 0 volts, it's a low. How do you tell what is high or low? You have to set a reference point. Which one is the lowest? That is your ground. A 0 point. 0 potential, from which all other voltages in the circuit can be measured. If we know a point in our circuit that has 0 voltage, then we can compare that to other portions of our circuit. For a circuit to work, you have to remember this. For a circuit to work, there must be an unbroken path from the power source through the components and then back to the ground. Once again, for a circuit to work, there must be an unbroken path from the power source through the components and the load and then back to the ground. Laging grounded or laging may ground sa aton mga circuits. Now, how does it work in circuits? In Tinkercad circuits. Let's look at that. Okay, so once again, we have your 5 volts from the 5-volt pin in our Arduino. That is our voltage source. Then we have your conducting path represented by this wire, the voltage rail right here, the positive voltage rail, and then we also have ground. We have this one, pin 13 connected via wire. Now, let me show to you. Let me stop this simulation and right here. Now, in this scenario, the cathode is here and the anode is here. So if it's not, anode can be presented in 2 ways. First, in its length, mas laba ang anode. We have a longer anode leg or a bent anode leg or a bent leg from the component. This one right here, it's represented as a bent leg. That is your anode, and then the straight one is the cathode. Now, we have your voltage source, we have your conducting path and the load, and it should return to our ground. Now, how does it work? We have your voltage source at pin 13. It goes through the wire, it goes through this component rail, then to our load, which is this LED. Then the other side, the cathode, is connected to a resistor. That resistor is connected to the black power rail, and that power rail goes back to that letter G and D, or in short, or when spelled out, that is the ground. We have a common ground level. Now, if I start the simulation, we have the code right here. All seems to work. But what if I delete that black line and start the simulation? By starting the simulation, even though we are supplying power, to the Arduino board, yes, the LED that is built in will blink because it is automatically connected to the ground, or it is designed to connect to ground. But everything else that is not connected to the ground will not function. In this case, we have voltage. We have a voltage source coming in from pin 13. We are bringing current through this wire and this component rail, but it will go through the anode, cathode, but there is no path or an unconnected path towards the ground or ground pin in our Arduino setup right here. So if we don't have a return ground, most projects on this one doesn't function because of a floating potential or floating ground. In this set right here, we have a floating ground. Now, if I return the connections again, if I were to repeat the connections, now let's use black. Once we return this line and create a common path for ground, we're back in business. It is now again blinking because we have a common ground. We have our voltage returning to our board in the form of a ground wire. Okay? It shouldn't be confused with grounding wire or grounding basically, but in our case, we have your connection from your voltage source all the way to the ground to make all of our components work. Now, this is the code that enables this blinking motion, blinking display. Now, on your own, I want you, after this lecture, after this video, I want you to tinker. I want you to change this number right here. You can go smaller, you can go bigger, and observe what will happen to our LED. How does it change the lighting behavior of this LED? Now, here's a fun one. Here's a fun one. We have here your Arduino, but this time there are 3 sets of LEDs and 3 sets of resistors that are connected into different pins. Now, let's use this as an example of looking at the void setup and void loop. Now, if you see right here, we have your pin 11, pin 12, and pin 13 having connections. Now, these are all digital pins, digital I/O pins, input-output pins. Now, in void setup, we have defined pin mode. The pin mode for pin number 13. This pin 13 is set to output, meaning it can output to a maximum of 5 volts. The same thing happens with pin number 12 and pin number 11. This portion of the code setups that pin 13, 12, and 11 are output pins. They are meant to output 5 volts. Now, let's run here for our tracing. We have your 5-volt rail right here in red. You have your ground connected from the Arduino and then connected to our negative power rail. And then you have your nephews. Why am I using nephew? Oh my, I'm using. It just came to my head. It just came to my head watching Modern Family. Anyway, this pin 13 is connected to our red LED and then connected to our resistor and then back to the black wire where it is then grounded. The same thing happens with pin number 12 and pin number 11. Pin number 11. All of these components are being supplied by their respective pins. They have their loads and all of it are returned to a common ground. Okay? Now, once again, we have your void setup. In void setup, we have defined that pin 13, 12, and 11, their modes will be output. They will be output pins. Now, on this side right here, we have your void loop. Let's understand these portions. It's a bit of a, it's long. It is a mouthful, but we can definitely understand it. Now, first, we have your function, you have your simple instruction, digital write. So, we will instruct something. We will instruct to write or output something. If we are using an output, if we are giving an output, we will be using the function digital write. Now, where do we output that? We go for pin 13. In pin 13, our output would be a high. Now, that pin 13, we can trace that to the red pin. By doing so, this line of instruction turns on our red LED. Next, digital write, pin 12 low. That pin 12 is connected to our green LED. By reading this line, it turns the green LED off. Now, this one, a bit peculiar, but it is a common practice where you have your delay, you have your instruction, and then there is this name that is being referred to. This right here is your variables. Our variable here is named time delay. By using this name, time delay, we're essentially using this word. Time delay is essentially a variable, just like X, just like Y. And the value of time delay is 250. It is understood that in this we are using the function delay, we are counting against time. So we have to delay it according to the value of time delay. Now the value of time delay is 250. The value of time delay is 250. So this will be, sorry for the wrong comments. We'll change that. Okay, let's stop the simulation and let's change the comments. By the way, in Arduino code or Arduino sketches, a double slash is a comment. It will not be read by the Arduino. It's just there for the developers. Something more like footnotes for the developers. Okay. So, in this case, we have time delay defined by the value of the variable time delay. Now, time delay is a variable. It is an integer variable, and the value of the time delay variable is 250. Okay, so after reading the first line number 14, and line number 15, after reading that, it will rest for the given value of time delay, which is 250. And then, after that time delay, let's go to the next lines. Digital write 13 low. 13 is our red LED. If I don't instruct it to change its value, it will stay at red. So, in line number 17, we are saying through the microcontroller that in pin number 13, we will set that as low. Again, when we have low is 0 voltage. Okay, next, digital write, it is an output. Let's output at pin number 12 a high voltage. That high voltage will eventually turn on the green LED. The green LED. Now, after that instruction, we have again your time delay. The time delay is at 250 milliseconds. After that time delay, pin 12 accepts a instruction to go low or to have 0 voltage or no voltage at all. Next, you have your pin number 11 becoming high or supplying 5 volts to the blue LED. Next, we will go again for another time delay. We will go for another time delay, which has a value of 250. And then, in digital write, number 11, it will be turned off because the value here is low. And then finally, another delay or time delay. Now, after all of these instructions, once it reaches the last line, it will go back to the start of the void loop. Okay, so it will read all of these instructions. After reading all of this, it will be restarted from the top, not from void setup, but rather the contents only of void loop. Again, void setup is instruction at the very start or at the very startup of the microcontroller. And then the void loop is the repetitive and clear instructions that needs to be repeated by the microcontroller. Okay, now here is my fun little exploration for you students. Now, this is the exploration that has to be done. Now, these are 3 pins, 3 different colors. Now, I want you to change the parameters and change the arrangements in void loop. Change the arrangements. Change the value of time delay. And then see how all of these lights react. Okay? So this is the base. This is the base circuits that I have built for every one of you. And in your Tinkercad classrooms, I want you to tinker around this, change the instructions, change the arrangements, and see how all of these lights will react. Okay? Nice, right here. This is the original function, but I want you to explore around how can we manipulate, how can we change the code so that we can see a different pattern in these blinking lights. So that will be the challenge for every one of you. I want you to copy and tinker this very program, this very circuits, along with the name, along with your initials and name. So it will be something like this. Okay, I'll be using my own name. So it would be, the name would be program me to blink CRB Gigantana. And then let's say I am in 10 Pascal. That will be the name. That will be the, let's say, yeah, that will be the name of the Tinkercad project. Okay, I forgot, and almost nearly forgot how to rename this. So you can click on this right here. By the time you copy it, it will become copy of programming blink, and then let's use the format. Program me to blink, and then your section, grade 10, let's say grade 10 Kelvin, and then what was the format that I've said? Oh, okay, this one. Okay, so we have CRB Cantana dash like this. Program me to blink, and then your initials, your first name initials, your middle name, and then your whole family name, and then dash 10 Kelvin or 10 Pascal. I am looking forward. So that will be your little bit of assignment, a little bit of an exploration. I want you to change the programming of the first and the second Arduino to explore what happens if you change the parameters. What if the instructions written in void loop is moved or copied over to void setup? What will happen? Or let's say you have an empty void setup. What would that happen? What if you define the values wrong? Or in our case, for this one on the multi-LED, what happens if I go 100 to 50? 500. What if I change these values? Okay, all of that you can explore around the Tinkercad classroom. Tinkercad circuits. Okay, every time you copy and tinker on all of these circuits, I will be seeing that, and I will be taking note of everyone that has tried to explore and copied to their own accounts. For those who have copied and tinkered on their own, I will be taking note of your outputs. They are all displayed automatically. You don't need to submit, don't need to give another link. As soon as you work on it, it will be saved and viewable on my end. Okay, so that's it for Creative Technologies 10. I know it's a bit long, it's an hour-long lecture, and it's a bit of a looping thing, but we'll make it happen. We'll try our best to learn despite this awkward and different situation. Okay, so once again, have a blessed day, everyone.